So Walter Baade uh, and Fritz Witzig, when they were studying the supernova, they had an idea there might be more than one type. Baade, in particular, thought there were like 5 or 6 different types of supernovae, and so later astronomers came down to the idea of two essential types. They call them Type One and Type Two. The big difference was Type 1, there was no hydrogen in the spectrum. Type 2, there was hydrogen in the spectrum. And so these are the two main types of uh, type 1A supernovae. And there's actually going to be type 1A, 1B, 1C, and so forth. There's more than one type of type 1. Is basically when a white dwarf star exceeds the Chandrasekhar limit and explodes. And this was the carbon detonation supernova. It can happen when you dump extra mass on the white dwarf. It can happen when two white dwarfs run into each other. So either way, the white dwarf is mostly made of carbon and oxygen, and so there's essentially no hydrogen or helium spectral lines because there's no hydrogen or helium in the white dwarf, and so that gives you this sort of characteristic spectrum that you see, and so that's your type one supernova. Now, type 1A supernova turns out to be very important because a type 1A supernova, because you always get a white dwarf that's about the same thing, then they all have the same sort of spectrum. They all have the same kind of brightness. And so you can use that as a standard candle. A type 1A supernova is as bright as another type 1A supernova within reason. There's more than one way of doing that, as I said, and so that will give slight variations. But as long as you understand those variations, then you can use that as a standard candle. You know how bright it's supposed to be, and you can see a supernova from all the way across the galaxy, or all the way across the universe, in fact. And so it's so bright, and so that way it gives you a way of measuring distances. Now, type 2 supernova, this is generic, really big star blowing up. And since the core collapses, but the outer part still has hydrogen, then you have a supernova that has lots of hydrogen in the spectrum. It's not as bright as a type 2 supernova because some of the energy, or type 1 supernova, because some of the energy is used up in blowing away the outer layers. So you get this, light curve that you get the light curve that you get is characteristic of this, and so the core blows up, releases an enormous amount of energy, and blows up the star. We know a lot more detail about that, but for this class, we're not. Type 1b supernova. This is another big star that blows up, but it is a really big star, a supergiant that the stellar wind has blown away some of the outer layers. Now, the outer layers are mostly hydrogen and helium, so if you blow away most of the outer layers where more of the hydrogen is, then there's not as much hydrogen, and so what happens is when you get a supernova here, you're not going to have the prominent hydrogen spectrum. So that makes it a type 1 supernova. Remember, that's one that has no hydrogen. You do get helium because there's still helium in that shell around the core, and so you get a helium spectrum. So a type 1b supernova is in fact another type of supernova. Type 1c supernova is another big star that blew up, in which the somehow you've blown away the outer layers, you've blown away the hydrogen outer shell, you've blown away even the helium shell, and what's left is a core that's got stuff beyond helium blowing up. And so it looks very, very similar to a type 1A supernova spectrum, but the light curve is different. The spectrum is a little bit different. It is a type 1 supernova because you don't see the hydrogen, but it's really because of a big star that blew up. And so you look at this and say, well, you got type 2, type 1A, type 1B, type 1C, and so that makes it look a whole lot like, well, you've got 4 different types of supernova. Well, that's much closer to what Baade was thinking. We think that your typical supernova in a typical galaxy like the Milky Way has about 1 or 2 supernovae per century. Now that's on average. The statistical average. So sometimes you get some centuries you get more, some centuries you get less. I mean, you could have two supernovae in the same week, uh, 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 but this is a statistical sort of thing. But generally, it's about one or two per century. Well, having said that, it was an interesting thing that when I first started astronomy, they kept saying they thought there ought to be one or two per century because other galaxies that are similar to the Milky Way were having about that many. But the last supernova visible in our galaxy was one that Johannes Kepler had seen in 1604. Now that's only a few years after one that Tycho had seen, also in the early 1600s. So, like I said, you can have a couple in a row there. So, just a statistical fluke. So, it could be a statistical fluke that some time goes by before you see another one. But this was getting kind of, a little bit worrisome that it was so long because here it was. I was in graduate school and we had not seen any supernovae since 1604, and so that's over 3.5 centuries. And so, well, there is evidence that the Milky Way has had supernovae, but you don't see them because interstellar medium blocks the view. And all this changed. The last naked eye supernova in 1604, and I was in graduate school in 1987 when all of a sudden there was a new supernova. And the new supernova was actually not in our galaxy, but in a galaxy that's orbiting around our galaxy, a little small satellite galaxy. And so it was the first supernova discovered in 1987. So that was supernova 1987A, the first one discovered that year. And it was discovered in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way. And it was discovered actually by a graduate student, Ian Shelton, who was in South America at an observatory working on his PhD, and looked up and looked in the part of the sky where he was supposed to be observing with a telescope in a little bit, and he saw, wow, there's an extra star there. And so that became a supernova. Now, of course, the trick was reporting this, get the word out that we discovered a supernova. So turns out that the observatory was kind of cut off from the rest of the world temporarily by poor communications in Chile. And so he had to travel to the nearest town that had a telegraph office to send word back to the United States, where it flashed across the internet, and everybody heard about the new supernova that was being discovered. And so it was 51,000 parsecs away in the Large Magellanic Cloud. So that turns out to be over 165,000 light years away. So here it was, Large Magellanic Cloud, 165,000 light years away, and he was able to see it with the naked eye. It gives you an idea as to how bright this supernova was. Now, the other interesting thing was the supernova was called as it was still getting brighter. Most supernovae are discovered near peak brightness or just after peak brightness as they're starting to fade. And so this star was also the very first one that was close enough that we'd actually had a photograph of the star ahead of time. Remember, this was his dissertation study, was this part of the Large Magellanic Cloud, and so they already had a photograph. The star that blew up was Sandy Lake minus 69 degrees 202A. That's just a catalog number. Now, the weird thing was they had always expected a supernova to be a red supergiant star in the last stages of its life. This star was a blue supergiant. So that was a little bit surprised. It did not get quite as bright as they anticipated. Another sort of surprise. And so it was like, well, what's going on here? We had the wrong kind of star that blew up. And maybe this was like a horizontal branch star that blew up instead of a red supergiant. So what happened? So they started studying this, as they started studying it, they realized that it got bright and started dimming. And as it was dimming, interestingly enough, after it had been dimming for a number of days, there was a little bump in the light curve down there, in which it momentarily brightened up again. And then a weird thing happened. When the supernova went off, it was a classic type 2 supernova. Had hydrogen in the spectrum. But towards the end here, became a type 1 supernova. No hydrogen in the spectrum. So this was weird. And they said, well, this is like, we didn't expect anything like that. Supernovae aren't supposed to do this. And so why a blue supergiant? Maybe large magnetic clouds have different metals. Maybe something weird is going on there. Maybe it exploded as a horizontal branch star before it could expand. And maybe there's something else we don't know. When the Hubble telescope looked, it saw that surrounding the star that was exploding, that thing in the middle right there, that is the exploding cloud of gas. That ring surrounding it was gas given off earlier in the life of the star. Remember, it is a red supergiant. Okay, and or at least it should have been a red supergiant, and that gas would have been given off as the red giant wind. Okay. Interestingly enough, on the same day that the neutrino, that Ian Shelton discovered the thing exploding visually, neutrino detectors that were looking at the sun's neutrinos suddenly got a blast of neutrinos from the supernova. From 165,000 light years away, it gave more neutrinos than the sun, up just 8 light minutes away. That means an unbelievable amount of neutrinos had to have been given off. Somewhere in the neighborhood of 10 to the 58 neutrinos. That's a huge number of neutrinos. That means almost 90% of the supernova's energy was given off in neutrinos, not in the explosion, not in the light given off. And so neutrinos turn out to be a hugely underestimated part of what makes a supernova. Now, this was a weird supernova. It was a blue supergiant that blew up. But in 1993, another one blew up. Another supernova, and this was in the galaxy M81. And so we have a picture on the left here. The picture on the right shows an extra star there that's sort of between those two stars right there. And that extra star is the supernova. And this is one that I studied when I was in graduate school, collected data on it. And the star suddenly blew up, and the thing is, they actually had a picture of it too, because this is a famous galaxy to get pictures of. And that also was a blue supergiant. And it also had an interesting thing that as we were collecting data, I actually was one of the first ones to notice. And if you actually Google supernova 1993J, there's my name in the data there. But I was one of the first ones to notice that it started brightening several days after it peaked. It started dropping off, got brighter. I did not have the equipment to make the measurement, but shortly after I made the measurement that was getting brighter, another observatory made measurements that showed that it had lost the hydrogen in the spectrum. So it's another one of these stars that started off as with hydrogen and then not hydrogen. So that suggests maybe it is a new type of supernova, a type 1-2 supernova. And so that adds one more type of supernova to the types of supernovae that are out there.